Hello everyone, in this video, I'd like to introduce our paper titled HPCClusterScape, Increasing Transparency and Efficiency of Shared HPC Clusters for Large-Scale AI Models. After the launch of GPT-3, many companies have been releasing large language models. This trend has led to an increased demand for high-performance computing clusters to accelerate model development workloads. As many of you might know, GPU-based HPC clusters are not only expensive to purchase but also costly to maintain. So the question arises, how can you optimize the efficiency of high-cost HPC clusters? Typically, when an HPC cluster is set up within a company or academic institution, it's shared among its members and involves two main stakeholders, the researchers and the operators. Operators are responsible for scheduling the submitted jobs efficiently, monitoring the cluster status, and diagnosing any issues in system. Researchers submit jobs for model training, wait for resource allocation, and monitor the training process and system usages. So what are the requirements for efficiency of shared HPC clusters? For operators, it's crucial to monitor the cluster status, minimize fragmentation during job scheduling, and optimize GPU and server I/O for machine learning models. For researchers, it's essential to monitor the training status and optimize the performance of their experiments. This means maximizing the utilization of allocated resources to complete their job fast. To achieve this, it's necessary to use an appropriate amount of resources based on the size of their model and data. However, achieving these requirements is not straightforward. From an operational perspective, complex scheduling policies are needed. Considering the varying scales of machine learning jobs, the unpredictability of their completion times, and the physical network topology of GPUs to avoid communication bottlenecks. From a researcher's perspective, large-scale training requires distributed computing with collective communication, which can introduce various engineering challenges. During such processes, issues like hardware malfunction can lead to an uneven distribution of workload across individual GPUs. This can subsequently cause bottlenecks when synchronizing computation results. Furthermore, for most researchers whose primary focus is on model research, might struggle to pinpoint the exact cause when problems arise in distributed training. Based on these challenges, we formulated two research questions. How can assist cluster operators in monitoring scheduling status and configuring complex scheduling policy? How can assist machine learning researchers in detecting and diagnosing potential issues on large-scale AI model trainings? To address these questions, we designed HPCClusterScape system. It collects data on cluster resource status, scheduling pool status, and individual GPUs usage. Using this data, HPCClusterScape facilitates exploration and analysis of the cluster resources at both macro and micro levels with three main visualization components. First is the cluster overview component. It's an exploratory visualization tool designed to allow both researchers and operators to monitor the GPU resources according to their respective objectives. We utilized unit visualization to represent each GPU as a square mark. Users can add various data attributes for grouping units through a card stack UI. By drag-and-drop interaction, they can define hierarchies between groups. We also provide layout operations that allow for detailed adjustments of group container size and alignment. These are examples of various monitoring views that can be figured using the cluster overview tool. Operators can set up views to see which projects occupy the most resources and their utilization percentage. Meanwhile, researchers who are planning to submit jobs can monitor scheduling status to see resource occupancy and rating jobs by GPU type. The second component is designed for historically identifying abnormal resources or experiments. Users can add conditions for detecting anomalies, which we've termed violation rules. For example, if the 95th percentile value of GPU utilization recorded during training falls below a user-defined threshold, it is considered that there was an issue with the resource usage of that experiment. Depending on the zoom level, the tool highlights the specific experiment or GPU. Before delving into the last component for large-scale training diagnosis, I'd like to first explain why diagnosing problem is challenging. Large-scale training inherently requires multiple GPUs and involves distributed processing of data or models. Distributed tasks necessitate synchronization. If some workers experience delays, others are left waiting. When such scenarios repeat throughout the training process, it not only severely slows down the training speed, but also impacts the overall efficiency of the cluster. The challenges lies in determining whether these issues stem from the training source code or are due to GPU hardware problems. Therefore, we designed a diagnostic tool to visualize these issues, enabling researchers to more easily identify problems. To quickly determine if system usage metrics are skewed on certain workers, we represented each GPU's usage pattern using small multiples. This is an example of a training experiment using 8 GPUs. Based on the GPU usage data, we provide a distribution preview to show whether resources have been used evenly from the past. Additionally, we offer a usage pattern preview to display changes over time. Furthermore, through time series data clustering, we aim to assist in detecting additional issues like workload imbalance by highlighting GPU groups with similar patterns. I briefly introduced the deployment and evaluation process. To validate the applicability of HPCClusterScape, we deployed the system on an HPC cluster composed of thousands of GPUs, which is operated by a company with an AI research organization. We conducted case studies and interviews with in-house operators and researchers. I'd like to share the key insights we gained from this process. By transparently displaying the cluster usage and scheduling status, we observed improved collaboration between operators and researchers. Through the cluster overview, researchers actively reported scheduling issues to operators. In turn, when operators suspected hardware issues in ongoing training experiments, they collaborated with researchers to address them. We were able to detect cases such as workload imbalance during distributed training through our diagnosis tool. However, to pinpoint the root cause of the issue, users needed third-party profiling tools, which stands as a limitation of our research. Nonetheless, the significance of HPCClusterScape lies in providing high-level insights into potential problems. Lastly, we faced challenges during the evaluation phase. As we deployed and evaluated our system on an actively used industry cluster, various factors like scheduling policies and resource demands changed dynamically. This made it challenging to control and precisely measure the impact of visualization on cluster efficiency, leaving a limitation in our study. In conclusion, our research defined the requirements and challenges for HPC cluster efficiency, targeting two user groups, researchers and operators. We proposed an exploratory data analysis tool to monitor HPC clusters and an analytical tool to diagnose problems in large-scale deep learning training. Furthermore, we deployed our proposed tool on an industry-scale HPC cluster, verifying its applicability and effectiveness in real-world scenarios.